All right, so let's start with the lab. Any questions on the lab?
Yeah.
Yes.
Okay.
Okay.
On the number 17, just all the vectors. I want to make sure I got all of them that I need to.
Okay.
The draw free body diagram.
Okay. So here's this rubber stopper, right? It's going around over my head. So what's one force that's acting?
Gravity. Centripetal.
How do you know that there's a centripetal force acting?
It's not.
It's moving in a circle, right? So you're dealing with trial one, right? So go to trial one, find the value of your centripetal force. Which direction does it act?
Inward.
Okay, there's one. What's another one?
Gravity.
Which way is it going to act?
Downward.
Down. Okay? You know the mass of your stopper in trial one. Yes, you know your gravitational acceleration on this rock that we're on. Can you find the gravitational pull between the stopper and this rock? Okay? Is there anything else?
Shouldn't there be a force opposite centripetal? Like, if there's a force, should there be an equal and opposite?
That's what the rubber stopper is going to feel. Because of the fact that that's going to be your action-reaction force caused by the end of the string. Because if that was the case, then if you look at the Earth orbiting, then there should be something like pushing the Earth out that balances out the inward force of, yeah. But that's where that action-reaction takes place. Anything else? Your answer to number 16 should be a not-so-good GPA. And should very much be less than the weight of the person, which is a cool thing, because if the centripetal force needed for us to stay on the spinning rock is greater than the gravitational force, we couldn't be here. I mean, like we would all go flying off, just like the quarters went flying off the green spinny thing. So if that answer to number 16 is bigger than what you get when you take his mass times 9.8 meters per second squared, we wouldn't be here. We wouldn't have oceans. All of the water would go flying off of the Earth because of the fact that the Earth would be spinning so fast that we couldn't hold an ocean. So that's what allows us to have oceans and us stay on here, is that because we're spinning, and it's a decent clip. Okay, we're going like 400 and some odd meters per second right now, but it's still not a big enough centripetal force that gravity can't provide that value. Otherwise, we'd have to like walk with our shoes tied down, but we would never be here to begin with, so it's kind of a moot point. So, anything else? Going what? Great.
The homework?
Huh?
The homework?
We'll get to the homework.
Oh, okay.
Okay, anything else on the lab? Once, twice sold, to make sure that you have labeled each graph so that I know exactly what your graphs are. None of them should involve a straight line. They should all be curves. Okay? So, if I draw like a curve of best fit instead of a line of best fit. None of these are linear relationships because they all involve the square. Okay? All right, great. Talk to me about the homework.
Okay, so let's see. It was I think it was it was the last one on B. I didn't know what is an amobia.
An amoeba?
Amoeba.
It's a small single cellular organism.
Okay, so for that one, did you just divide by 9.8?
Oh, no. You're asking two different things here.
Okay.
Okay, so let me give you this hint. Every answer on number 9 should start with a 4.
Okay.
Okay? Every answer should start with a 4. So on 9A, you're figuring out what your acceleration is in meters per second squared, which should be a pretty big number, like something times 10 to the 4th. Okay? So again, you get the G's, you're going to take your answer from A and divide it by 9.8 meters per second squared.
Yeah.
That's it.
Oh, okay.
And then to get your answer to C, centripetal force is mass times your centripetal acceleration. So on E, you're just taking the mass times your answer from A.
Oh, okay.
Go with that.
Yes. Thank you.
Your answer to number 7, the centripetal acceleration of our rock as it goes around our star, should be a pretty small number. Okay? Should be a pretty small number, which is a cool thing. Because if that answer was really, really big, we wouldn't be here having this discussion because the centripetal force needed would basically rip the Earth apart. Okay? So that's a cool thing that's a pretty small centripetal acceleration. Okay? And if you, by the way, on number 8, let's say that you have an answer, which isn't your answer, but let's just say, let's say that you have an answer of 0.002. How many significant digits does that have?
1.
1. You will not get full credit for an answer like this, because that only has 1 significant digit. Oh. Okay. Your answer to number 3, and this is an ish, should be something around your current age. That's an ish. Okay? That's an ish. Not old enough to buy beer, but something around your current age. Your answer to number 4 should start with a 4. Anything else on the assignment?
It'd be a good number for number 2, the answer.
This is an ish, a big ish, around 1,000.
Okay, that's what I thought.
Yeah, that's an ish, but it's around 1,000. Mad Max? Are you not around 1,000?
I did something really wrong.
What did you get out of curiosity?
I'd rather not say.
Say it. What did you get?
3.2.
3.2. Okay, so what Max is saying is that
Yeah, well,
A plane-
I knew that was wrong. I
a
was going
plane
to
which
talk
is
to
traveling
Eric.
close to the speed of sound is going to turn in a radius about as far apart as my arms are.
I knew that one was wrong. I will say that. I knew that was wrong. I didn't know what I had done wrong.
What would be the G's on that?
Oh, it's just
A lot.
astronomical. Great.
Number 6.
Keep you
What
dying.
is the factor? I was torn between gravity and friction. So I don't know. That's what I'm saying.
Okay, gravity would be
I think
what
that's
holds the Earth in orbit.
Okay. I thought I was creating like a gravitational pull if you're like running in a circle like that.
Yeah, but to a certain extent, you could make the
Okay,
argument that
that was my
without
problem. I
gravity,
just
you
didn't
couldn't have
swear
friction
that.
in that situation, okay? Because you would just push off,
There we go.
you go floating up. But it's the friction is
Okay.
what's causing that.
Understood.
Okay. Anything else? Going,
Number 8.
Vonda. What, number 8?
Yeah.
Okay? So on number 8, here's the deal. So you want to compute the inward force. So you're trying to find the centripetal force, right? True?
Yes.
So you know centripetal force, in this case, what I would recommend is I'd go mass 4 pi squared r over t squared. Okay? That's what I would recommend. Now, you have everything, but I didn't directly give you the value of period. But on that one, I told you that he's spinning at 2 revolutions per second. So 2 revolutions per second, is that frequency or period? Vonda?
Frequency.
Yes, because that's an event per unit of time, right? And so yesterday we said, and it's on your equation sheet, that period and frequency are inverses of each other.
I don't know, what
So you have 2 revolutions per second, right? So that's your frequency. So take the inverse of that, that becomes your period, and put that in there. Does that make sense, Vaughn? Okay.
When we're running the unit for that, would you like that as seconds over revolution?
Technically, it's seconds per revolution.
Yeah. Okay, because that's how I remember.
Michael, I want to tell you how to do it. So here's the deal. So you have a tire that's spinning, right? So as the tire spins, does this pebble want to travel in a circle?
Yeah, 2 times 9.
What does the pebble want to do? Wants to fly off in a straight line, right? True? So you know that centripetal force equals mass v squared over r. You've got the frictional force is what's creating the centripetal force. You can find the radius. You know the mass of the pebble. Solve for velocity. Anything else? Going once, going twice, sold.
Whoa.
That was fast.
Go to the Renaissance Fair.
Huh?
What's wrong with going to the Renaissance Fair?
I wouldn't go there on your
I bought a sword there. It was awesome.
You bought a sword?
I bought it.
Like Excalibur or
No,
what?
I forgot the name. What they're called? They're the samurai swords. I completely forgot the name.
Katana?
Katana. Yeah, I bought it.
That's something that you buy at a Renaissance fair?
There's an
Buy a
entire,
claymore. Buy something else. I don't know, man. You buy a katana?
there's an entire tent of katanas, so I bought one.
What'd you have to get for it?
Huh?
What'd you have to get for it?
30.
Really?
Yeah, I talked them down to 50. Probably because it was like raining that day, so they didn't have very much business.
Yeah.
Okay. 30
All right,
right now.
back to our story. So let's talk about something relevant. All right, so let's say I've got this rubber stopper swinging around over my head. As it goes around over my head, does the amount of centripetal force change? No, why?
Constant velocity. So
Well, it's not, it's constant speed. Is the velocity changing?
Yeah.
Is the velocity changing?
Yes.
How do you know?
Change direction.
Changing direction. The magnitude is staying the same, but it's still accelerating because I'm changing the direction, right? So when you look at centripetal force equals mv squared over r, everything is going to stay the same as this thing goes around. No point is going to be more likely to break than the other point because it's all the same amount. However, what if I take that same rubber stopper and swing it around in a vertical circle like this? Okay? Then do you think there's going to be a change in the amount of tension on the string?
Yes.
Mary, when do you think the string would be most likely to break? At the bottom, or at the top, or on the sides? Or nothing?
At the bottom,
You say that with absolutely no confidence.
correct.
You should have confidence in your answer.
At the bottom,
At the bottom. Very good. Now, why?
because of gravity.
So gravity only pulls on it at the bottom. Gravity doesn't pull on it at the top.
No, it pulls on it all the time.
Okay?
Yeah.
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 So why is it more likely to break at the bottom? Your answer is right. And it does involve gravity.
Because as it goes further towards the bottom, does the velocity get?
No, velocity is going to stay the same. Great.
Okay, so
Well, I feel like ping pong.
as that's keep doing that. Yeah.
Okay?
As it goes up, as the rubber stopper goes up, its force applied is now, its force net is now lower, so the tension's lower. So when it's going down, it has no force applied, and all of its force is going down along with the force from gravity as well. So then that force net is stronger at the bottom, making the tension stronger.
Now,
The
Okay.
centripetal force.
you're 3/4 right, but you're using your terminology wrong.
Yeah, I know.
Madeline,
The centripetal force at the bottom is higher than at the top.
no. Why?
What
Velocity is going to stay the same
Yes, because the circle.
because of the circle.
Yes.
May the circle be happy. No. Okay. So let's look at this. Let's say that I've got the coolest physics room, which I do, but let's say it's even cooler. And let's say that my physics room is attached to a huge pendulum. Okay? And so you all are sitting here, right? So here's Madeline sitting here, right? And she's sitting here. And right now, as she sits here, okay? We're not moving at all. What forces are acting on matter?
Gravity.
Gravity and force normal, right? So I've got some Fg and I've got some normal force. Okay, this is what you all are used to experiencing, right? Okay. Now, imagine that I'm going to take this room and I have the capacity to make this room start to swing back and forth. Okay? It's like I'm this huge pendulum. So my entire room starts to go back and forth like this. Okay? Back and forth, back and forth. When she's at the very bottom of the swing, how are you going to feel? Heavy, light, or no change at all?
I feel normal, isn't
Bree shakes her head no. Bree, you're sitting right beside her. How are you going to feel?
Heavy,
Why are you going to feel heavy?
because there's more gravity acting on you?
Okay, but when I'm not swinging, I feel normal. So
Yes.
when I'm out where I would be when I was swinging, why would I not feel normal?
Okay, hold on. When you get to the bottom of this swing, what does your body want to do? You're at the bottom, you're at the very bottom of the swing. What does your body want to do?
Stay.
Go in a straight line.
It wants to go in a straight line, true? So are you going to accelerate? Are you going to undergo centripetal acceleration at the bottom of that arc?
Yes.
Yes, why?
Just don't go in a straight line.
So you're traveling in a circular path. So you're going to feel two things. You're going to feel the normal force, which is balancing out the gravitational field, right? Plus, you're going to feel the additional force that it takes to make you travel in a circular path, because your body doesn't want to travel in a circular path. So at the bottom, what you're going to feel are two things. The total force that you're going to feel, right, is going to be the centripetal force needed to make you travel in an arc, and the normal force, which is balancing out your gravitational field. So imagine this. Let's say, which would be cool, but let's say that I could shut off gravity right in this area as this thing is swinging, in a vertical plane. If I could shut off gravity just in this area, would the tension in that string ever change?
No.
No, because it would always be the same, because there would be no gravitational field. In that regard, it would be just like me swinging this thing over my head. Okay? The tension would always stay the same. So if I could swing this thing in a vertical plane, then without gravity, there would be no tension. There would be no change in the tension, because the only force that I would have to provide is the centripetal force. Now, what if I just hold the stopper? How much tension is in the string right now? Enough to balance out what? Gravity. So when this thing is going into the bottom of this arc, that tension has to do two things. It has to balance out the gravitational pull, which is trying to keep the rubber stopper down. So this is where gravity is part of what Mary said. Okay? Now, what you were saying the applied force. Okay? What you meant to say was the centripetal force.
Yeah.
So at the bottom, the centripetal force and the normal force are having to be provided by this string. Now, at the top, okay, at the top, assuming that it's going fast enough to complete the loop, at the top, does there have to be some centripetal force?
Yes.
Yes. Why?
Circle.
It travels in a circle, right? Because if I go to the top of that loop and there's no centripetal force, it goes flying off, right? So at the top, there still has to be some centripetal force to make it travel in a path. But now, here's the difference. When you're at the top of that loop, it takes a certain amount of centripetal force to make it go in a path. But in this case, gravity is helping you out, okay? So you're going to feel lighter at the top because of the fact that gravity is providing some of that force. At the bottom, you're getting the gravitational force and the centripetal force, and that's where you're going to feel heavy. So let me show you a clip from a roller coaster, and you can actually kind of this is the cool thing about the human body is that you'll watch this and you'll see what I mean.
Cool biology.
That's kind of a biology gig. Huh?
I said it's almost just as fun as it is.
Almost.
Yeah.
Now, you're at the bottom of this arc. How are you going to feel? Heavy. Because you're going to feel weighty, right? Because your stomach, which has mass, wants to keep going in a straight line. So, as you hit the bottom of that arc, there are two upward forces that have to act on you. And you're feeling the action-reaction to those forces. So you're balancing out gravity, which is trying to keep you down, but then you're also having to undergo centripetal acceleration because at the very bottom, your body wants to go in a straight line. So by virtue of the fact that you're traveling in a curved path, that means that that takes more force to make that thing move. Now, if you're just sitting there, this is where this gets a little bit creepy. Just a little bit. So let's say that you go to the amusement park and you're wearing a trench coat. That's a little bit creepy in and of itself. More importantly, you have a bathroom scale hidden inside your trench coat. It's a little creepier there. And so you get on the roller coaster, hopefully you're sitting alone, and you take the bathroom scale and you put it underneath your butt and you sit down, okay? And you look down and let's say this reading 100 pounds, right? So when you're just sitting in the roller coaster, not moving at all, the scale is reading 100 pounds, right? So you're at the bottom of that arc. If you were to look down, what do you think would be the reading on that scale? More than 100? Equal to 100 or less than 100? More. Okay? Because your body is trying to go straight and you're being pulled down by gravity. So at the bottom, you're going to feel heavy. Now, as you keep going, now, how are you going to feel going over the top of that arc?
Light.
You're going to feel light. Why?
Like
Your body wants to keep going. Exactly, Felix. Your body wants to keep going. So if you were to look down on that scale, going up over the top, what's it going to read?
Less than 90.
It's going to read less than 100. It might read 90, 80, something like that. Okay? So what's the only time it's going to read exactly 100?
when you're flat.
When you're not flat and not accelerating vertically like up and down.
Yeah.
Okay. Now there we go.
I wish our roller coasters lasted that long. I bet.
Maybe I could write a grant to build our own roller coaster here at Mays High School. We'd be like the only high school with our own roller coaster.
And the biggest solar system.
Yeah, well, gotta have that too.
And we could run a solar system to power the roller coaster.
Whoa! Like that. Either that or we'd have the freshmen that work pulled up. Okay.
The only high
Really
school
gotta earn your diploma here.
leaver.
So,
There's a lot of private schools.
When you're at the bottom, okay? When you're at the bottom, the total force, or what net force, however you want to think about it, is going to be the sum of two things. It's going to be the normal force, which is balancing out gravity, and the centripetal force to keep you moving in a path. So this is why at the bottom, you're always going to feel heavy, okay? You're always going to feel heavy. Now, up here at the top, if we add them at the bottom, what do you think we're going to do at the top? Subtract them. Oh, so this is at the top, and this is on the lecture notes that I've given you. If you ever read a set of lecture notes, read these lecture notes. This is why I kill trees, is to give you lecture notes, okay? So at the top, your total force is going to be force centripetal minus Fg. Now, here's what's important. Up at the top, okay, up at the top, this is the only time I really talk about feelings in my room. This is what you are going to feel, okay? This is what you are going to feel. So what you'll see here in just a second is a video that shows how this deal plays out. So let's say that, where did my rubber stop?
Threw it over
Oh, I
there.
threw it over there. Yeah, my bad. Now, so as this thing goes around in a circle, right? Is there a minimum speed I have to complete the loop?
Yeah.
Yes, because if I'm going too slow, guess what? I don't make it, right? But if I'm going faster, then the string stays taut. So somewhere there's a critical speed where I'm just going fast enough to complete that arc, okay? Where if I have just the right speed, that means I really don't even need this string. It would be in a state of weightlessness. So what you can do is say, oh, okay, this I can set equal to 0. So what you'll see here is when you're in a state of weightlessness, and there's a company called 0G that sets this up. So this is going to be what you're going to feel. So if you want to feel weightlessness, you go, oh, 0 equals force centripetal minus Fg. You would feel like you are floating, okay? Absolute floating, like you were in 0 gravity. So here's the deal. So 0 equals force centripetal minus Fg. What can I do? Perhaps move an Fg over here? Radical concept? Fg would equal force centripetal. Now, how are you going to calculate your gravitational force? What two things do you need? Mass and
acceleration.
Gravitational acceleration. Now, over here, I'm going to have mv squared over r. Now, what's going to happen to your mass? It's going to cancel out. Okay? Now, what I'm going to do is I'm going to solve for radius. Excuse me, I'm going to solve for velocity by multiplying by this. So what I get is v equals the square root of
Gravity times.
Girth. So this is kind of like the dog equation, square root of girth. Okay? So what this gives me is the minimum velocity that I need to be in a state of weightlessness. Now, what you'll see in the video is that this could also be anything that you want it to be in terms of what you feel. So in the video, they're going to simulate Martian gravity. Martian gravity, you feel 1/3 of what you feel right now. So if you want to feel Martian gravity, okay, what you're going to feel is 1/3 of what you feel right now. Okay, you would feel 1/3 of your normal weight. So your arm would feel 1/3 as heavy as it normally does. Now, that still equals force centripetal minus Fg, because this only works at the top. It doesn't work at the bottom. This only works at the top. So what I can do is move this over. So 1/3 plus an Fg gets me what?
4/3.
4/3. So this is going to be 4/3 mg, which equals mv squared over r. These cancel out. V equals the square root of 4/3 girth. Now, you're also going to see in the video, they simulate lunar gravity. In lunar gravity, it is 1/6 your normal weight. So in lunar gravity, the only thing that changes is that this becomes 1/6. So this is the only thing that you can change in this equation. This is what you feel. And it's always going to be a multiple of your gravitational field that you're used to experiencing. So it's 1/6, it's a third, it's whatever it is. Okay? And then you're always going to solve for that velocity. Got it? Now, let me show you the video on that one.
So, was that F total, F?
In the early days of space exploration, NASA developed a technique to recreate zero gravity, the notorious vomit comet. Because the weightless effect of microgravity is nothing more than a continuous free fall, it's possible to simulate it by flying an aircraft in a huge arc or parabola, which, for short periods of time, allow those on board to float as though in space. But the stomach-churning ride could spell trouble for some people. Once in the air, we climb up to 7,300 meters to start the first of 12 parabolas. Here we go. This very first parabola is going to be Martian gravity, so 1/3 my body weight. I can immediately feel myself detaching from the floor of the plane. Are becoming increasingly severe. Basically, I'm skydiving inside the aircraft. That is so strange! Oh, wow! Go Team Silver!
Okay, so here's basically the math the pilot is doing. So, like he wanted 1/6 Martian gravity, or excuse me, 1/6 of your normal gravity, which is lunar gravity. So basically, you have 1/6 Fg, and this only works when you're at the top of this parabolic curve. You can't do it at the bottom because you're adding at the bottom, so you cannot experience weightlessness at the bottom. It can only occur at the top of this flight. So basically, if you want lunar gravity, you're going to feel 1/6 of what you feel right now. So that's still Fc minus Fg. You move this over, you get 7/6 mg equaling mv squared over r. Masses cancel out. You get v equals the square root of 7/6 girth. So if you know the radius of that parabolic curve, this just tells the pilot how fast he has to be going into that curve so that you feel 1/6 of your weight. So if you wanted to actually feel your weight even at the top of that curve, you would just set this equal to Fg. So, but then really what's the point? Because then you're just feeling like you feel right now. But here's the reason why it's called the vomit comet. Because you're flying in these huge sinusoidal curves. So you get about 20 to 30 seconds of weightlessness up here at the top. Okay? Then you're at the bottom, then you're going to feel really heavy because then you're adding them at that bottom. And then you're back to a state of weightlessness, and then you're back to feeling really heavy. And so this is why it's called the vomit comet, because so many people hurl because of this continuous going up and down and up and down. Hunter?
Can any aircraft do that?
Oh yeah, any aircraft can do it. Yeah. Right?
Did you say that's 7 gur over 6?
Yeah, so it's 7/6,
Okay.
gur.
And my question earlier was like the F total.
Yeah.
How come, like, I don't know, maybe I misunderstood, but it was written both as centripetal force plus force gravity and then centripetal force minus force gravity.
No. At the bottom, okay, it's force centripetal plus your normal force because, and then at the top, you're subtracting the weight.
Okay.
So basically, you add them at the bottom and you subtract them at the top.
Okay.
Okay? All right.
pretty cool. You only get short periods of time, maybe 20 seconds, 30 seconds at a time, but it's just like being in space.
We're all gonna be facing that way, right? You're gonna kneel, and you're gonna try to crawl as fast as you can, okay? Okay? Alright, you're gonna have
Yeah, sure, okay.
Go, 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 go! Woo!
I can now better understand how difficult it must be to relearn every physical task during a prolonged spaceflight. Okay. That is just the most unbelievable experience. We're now completely weightless, able to fly like Superman. The constant pitching of the aircraft is pretty intense. And by parabola 10, the effects are starting to hit me.
Okay, that's when we get into biology, and that's when we're going to stop. Y'all know how I feel about
You
biology.
complimented biology twice today.
Oh, it is cool, but I just don't want to see it. How about that? You know, biology is cool, but it's also horribly icky. So, stop that for a second.
Earhart parachuted out, okay?
Okay, whatever.
They still found female human
So
bones on
here's how
islands.
this works. So let's say, it's a simple demonstration, which is going to be similar to one of the questions on the homework. So here I've got like a cup full of water, okay? All right? And I'm going to take this thing, I'm going to swing it around over my head. So what I want to know is what's the velocity, minimum velocity I have to make this thing go around completely without me getting wet. So, the only thing I need is the distance from my shoulder down to the bottom of the cup, which is roughly what? Somebody estimate.
That's pretty far.
4 feet.
4 feet. Did you really say 4 feet?
I'm gonna say a good 3 feet. Okay, 2.5.
Okay,
No,
Nick,
Nick,
go
go higher and in meters.
Meter and a half.
Alright.
So 1.5 meters. 1.5 meters.
Okay,
Wait, what are we talking about? The shoulder to what?
To the bottom of the cup.
Oh. Yeah, meter and a half.
Okay. So, to get the minimum velocity, and this is going to be important, to get the minimum velocity, we're going to use v equals the square root of z, right? So, here's my arm, okay, there's my hand, there's the bottom, right? So, as this thing is going around, I want the absolute minimum velocity that I have to have. What that means is that that water cup would be in a state of weightlessness at the top. So, somebody take, we call it 1.5 meters, so 9.8 meters per second squared times 1.5 meters.
3.83.
3.8 meters per second.
Yeah.
So what that means is if this thing is going to stay dry, I have to be going at least 3.8 meters per second. Okay? That would put me in a state of weightlessness. So, with that said, that's really wet. Okay. Do this.
Here it is.
Oh. Oh. Oh.
Whoa.
Okay? Now,
Is it
It
glued?
scares me.
Oh.
it's not glued.
It looks so glued. Close. We should have Nick try it.
No, no. So, here's the deal. So clearly I made it around, right?
Well,
So, here's what I want, here's what you have to visualize. Here's that, and here's my arm, right? That's at the top, and then here we are at the bottom. So here's the cup, okay? So imagine that there's like a little thin scale that reads in newtons, okay? So if I want to make this thing complete the loop, at the top, when I take Fc minus Fg, I want this to be greater than or equal to 0. So by the virtue of the fact you said, oh, it looks like it was glued to the top, or it was glued to it, it's because I was making this total force be a big number, okay? So what that means is that I had to have this platform to keep that thing from going off in a circle. So when you get to question number 5, okay, so let me get you started on question number 5. So at the end of the day, it says, what speed must be traveling at the moment the force exerted by its body on the seat is half its actual weight. So when you get to number 5, you're at the top of the loop, right? You want to feel half your weight. So over here, you're going to put 1/2 Fg equals force centripetal minus Fg. Okay, this is what you're going to feel at the top. So I'm going to move this over here. I'm going to have 3/2 Fg equals force centripetal. So this is going to be 3/2 mg equals mv squared over r. Now, problem number 5, I did not give you the mass. Why?
You don't need it.
You don't need it.
It cancels out.
It cancels out. Okay, that's why I did not give you the mass. So we're going to work 8 and 9 tomorrow in class. So at least try and get 1 through 7 done, and we'll talk about 8 and 9 tomorrow because we're not out of time because of the quiz. So we'll finish that discussion tomorrow. Okay? Got it? Good, Brand?